Okay, let's begin with a discussion of constitutional isomers. Isomers are defined as chemically different compounds that have the same molecular formula. The most obvious type of isomer is a constitutional isomer, and these differ in atom connectivity. There are other type of isomers that are a little bit more subtle, and we'll cover them as we get to them because you'll appreciate the nuances that go with that type of isomerism when we're discussing the issues surrounding those more subtle types of isomerism. Okay, another fundamental thing about isomers is as the molecule gets larger, i.e. it has more atoms, there are more isomer possibilities. Okay, let's just take the simple case of this molecular formula C2H6O. Alright, there are two compounds that we can have that have this formula. Dimethyl ether, which is actually quite a toxic compound, and also a toxic but less toxic compound is ethanol. Many of you are familiar with this as the intoxicating ingredient in alcoholic beverages, so I say that dimethyl ether is toxic, whereas ethanol is intoxicating. Obviously, you can see from these two compounds that molecular formula alone cannot adequately describe a compound, and here there would be disastrous effects if dimethyl ether replaced ethanol in certain certain cocktails or whatever. Okay, so let's add one more carbon and go to C3H8O. Okay, here we can actually draw three isomeric compounds. Isopropyl alcohol, which you'll recognize as rubbing alcohol, N-propyl alcohol, which has a lot of industrial uses, and ethyl methyl ether. Okay, as we get more and more carbons into the structure, the number of isomer possibilities increases further. Okay, so constitutional isomers are the most obvious types of isomers, and they're the only types of isomers we will deal with for a while. Okay, let's look at something that's akin to isomerism, but isn't really isomerism. Or these may look like constitutional isomers to you at first, but they're not. Okay, and this is the issue of resonance. For certain compounds, if we were asked you to draw the Kekulé or the Lewis structure, there would be more than one correct answer. So let's say draw nitrous oxide, N2O, where nitrogen is the central atom. I can draw two perfectly acceptable Kekulé structures for using that set of directions. If I asked the class to do this on an exam, maybe half of you would come up with this structure right here, which has a nitrogen-nitrogen triple bond and a nitrogen-oxygen single bond and formal charges as shown, whereas another segment of you might come up with structure B, which has two double bonds from a central nitrogen atom and formal charges as shown. Okay, technically the connectivity in these are the same. It's one nitrogen surrounded by another nitrogen and an oxygen. We call this situation resonance. Resonance structures, they're not constitutional isomers because of the identical connectivity, but they differ in where we place the electrons. So resonance structures differ in the placement of electrons, but not atoms. Okay, if we ask for, or what does the compound look like, there's a way to actually take a picture of a molecule called X-ray crystallography. And if you looked at the structure of nitrous oxide, you would have to say it would contain some of the structure elements of both A and B. Okay, we would say that the true structure of nitrous oxide would be some sort of blend of the structures of A and B, and the structure here called the resonance hybrid would be the true structure. Okay, so if we notice one common structural feature in both forms is of course the central nitrogen atom with a positive charge, and that's going to be a feature in the resonance hybrid. They differ, these structures, in where they place the negative charge. B places it at nitrogen, at the outer nitrogen, and A places it at oxygen. So both the outer nitrogen and the oxygen would have a partial negative charge. Okay? To represent that something is a resonance structure, we would use this arrow here called the resonance arrow. So this is the resonance arrow, the double-headed arrow. When you see it going between two compounds, it implies that they're resonance forms. Okay, these two molecules are not equal. You might wonder, is one representation better than the other? And it turns out that in this case, A is a better structure than B is. Because A places the negative charge at the more electronegative atom. Okay, so oxygen's more electronegative than nitrogen, and the negative charge is at oxygen in A, and it's at nitrogen in B. So we'd say that in our resonance hybrid, it's not truly going to look like an equal contribution from A and B. There's going to be more contribution from A than from B. And I'm going to just caution you about one thing that you'll notice in this class is that we try not to write resonance hybrid. It's hard to depict the flow of electrons from a resonance hybrid. We're going to use the individual resonance forms to illustrate the progress of reactions, or something that we'll call the reaction mechanism as we go further in the course. So basically we don't like to depict these partial bonds that you see in the structure like this. It sort of leads to a lot of confusion as to where the electrons are located. Okay, if we look at how do we show the A and B interconverting, and again, interconverting is actually a bad word. They don't truly interconvert. It's just two different representations of the same thing. But organic chemists commonly use something called aeroformalism. And this is how we show that the electrons are moving here. Okay? So if you notice, as A turns into B, this lone pair of electrons is going to become the NO bond. Okay? And this, one of these bonding pairs in the triple bond is going to turn in to a lone pair. So we can sort of use these arrows here to signify that that's what's going on. Okay? And I have a web link on the Canvas page that goes to a more thorough discussion of aeroformalism, and we're going to use this throughout the class. Arrows have to start from an electron pair, which can be a lone pair or a bond, and they have to move all the way to the point where there's no hypervalency. Let's just imagine we move the first electron pair, but not the second one. Okay? Alright, so we start out, that's negative and that's positive. Alright, so just one arrow. Okay, so this gets us to this. And this has 5 bonds to nitrogen. And this is bad. So we have to keep moving the arrows in such a way that we never end up with a hypervalent structure. Okay? All right. So you'll appreciate this as we use it more and more throughout the class, and hopefully you'll get to understand it. And I always tell students, bite the bullet. Understand aeroformalism, and organic chemistry will be one of the easiest classes that you ever take. Okay, so here's a few compounds that we can draw as resonance forms. Okay, a simple one is ozone. Okay, so ozone, we can have 2 resonance forms here. Okay, and we can move the electrons like so, and we get it here, but you'll recognize that these 2 structures are technically equal to each other. So we refer to these as degenerate resonance forms, okay? You may wonder, why even bother to write that? I mean, aren't they the same structure? Well, technically they are, but it's important to recognize that there's resonance going on in this molecule, because when we look at the resonance hybrid, it tells us an important thing, that the middle oxygen has a formal positive charge, as it does in both resonance structures, but the negative charge is shared equally between the 2 outer oxygens. We say that the negative charge is delocalized. This is an important word in organic chemistry. And delocalization. Okay, we're going to use these words a lot, and they just refer to spreading, in this case, spreading the negative charge over 2 atoms instead of having it exist completely at 1. A similar place where this is important is in the acetate anion. Okay, so the acetate anion, we can write a resonance structure that's also degenerate, where we have the negative charge on the other oxygen. And if we look at the resonance hybrid, what we see is that the negative charge is also delocalized. And when we discuss acid-base chemistry later in this chapter, we're going to see that this is an important phenomenon. Okay, last case, this is going to be relevant in the last chapter of the first half class, Chem 313. But aniline. Aniline, there's some very important resonance interactions going in aniline. Okay, so the nitrogen lone pair here is delocalized into the benzene ring. And here is a good illustration of one of the principles I told you in bond line diagrams. When you have a charge, it's always a good idea to not use a bond line diagram in the vicinity of a charge. So I've scrapped the bond line diagram here. I think this leads us to a clearer picture. Okay, here we have multiple resonance forms. Once we generate this resonance form, you can see we can even write another one. I can put it down here, negative charge down here. And once we're here, we can do it over here, which technically is these 2 outer ones are technically degenerate resonance forms. But when you look at aniline, if we look at its resonance hybrid, okay, sorry about this extra line here. I see there's actually a fairly decent amount of partial negative charge character at those positions of a benzene ring, and that's going to be a major feature in the reactivity of molecules like aniline that we'll discuss when we discuss aromatic substitution It's chapter 12 in our textbook. Okay. And so I'd like to just in these next few slides summarize the rules for resonance, and then we're going to look at how to decide between two resonance forms which is the better resonance form. Okay, issue number 1. Two resonance forms must have the same connectivity. Okay, so here we on this compound on the left here, we can move the electrons like so. Okay, I'll move it over there so it is at the same place. There's already another electron pair. But here you see that the connectivity is the same. It's a nitrogen in the middle bonded to another nitrogen and also bonded to an oxygen. Okay, that feature is present in both of these structures. Okay, let's look at the structure over here to the right. These do not qualify as resonance forms, okay? So this carbon has one hydrogen. This same carbon has two hydrogens, okay? That means it's not resonance. Okay, if we look at this external carbon there outside the ring, we see two incidents where there's a change in the connectivity in the structure. So these do not qualify as resonance forms. The resonance forms have to have the same connectivity. Issue number 2, no first row boron to fluorine atom can have more than 8 electrons. Okay, so these two compounds here would be resonance forms, okay? It can have 6. There's only 6 electrons in this form here. It's better to have too few than to have too many. We can say it's like the old TV game show, The Price is Right. Okay, where you can't go over. All right, so let's look at this other one. We can delocalize the negative charge to carbon by writing this resonance form, but here we have 5 bonds to carbon, and this is not allowed. Okay, so this is hypervalent. Okay, that's the word we're going to use a lot in this class too. That means it has too many electrons. Okay, each resonance form must have the same net charge and the same total number of electrons. Okay, so these two compounds shown here are not resonance forms because the electron count is different. We'll just look at the valence electron count. There's 2, 4, 6, 8, 10, 12. There's 12 valence electrons there. Let's count here. 2, 4, 6, 8, 10. Here there's only 10 valence electrons. When you do a formal charge calculation, this last problem is actually kind of easy. Okay, you see that one of them actually has a net negative charge and the other has a net positive charge. Okay, so this is another issue. Each resonance form has to have the same net charge and the same total number of electrons. Okay. Let's look at which resonance form is better. Okay, the better resonance form has less charge separation. Okay, so when I look at this compound here, which is known as an enol ether, a resonance structure that I can write involves taking oxygen lone pair and making a structure that way. Okay, and here we have this resonance structure that has a positive and a negative charge. Okay, if you look at the actual structure of the molecule, the structure on the left is the better structure, and this is because it has less charge separation. If you can draw a structure that doesn't have any formal charges, typically that's going to be a better representation than something that does. I'm going to add something about this, though. This is the less important resonance structure, but this resonance form here, even though it's less important, is very good at explaining the reactivity of this compound. So even though a resonance form's not quite as good, we still can't ignore it. We can't ignore it. It can still be important in its reactivity profile. Okay, the better resonance form places the negative charge at the most electronegative element. Okay, and here we see two resonance forms. This is for an amide anion. Okay, and the resonance form on the left has negative charge at oxygen. The resonance form on the right has negative charge at nitrogen. And thus we would say this is going to be the more important resonance form right here. Okay? But I'm just going to caution you that you can't ignore this one. Okay? This is still important. It explains the reactivity. As far as like, how does this compound look? Well, it looks like this, okay? It's going to have the, if you took again, an X-ray structure, it would see more like a carbon-oxygen single bond, okay, and a carbon-nitrogen double bond. Okay, the better resonance form would have the maximum number of covalent bonds without violating the octet rule. Okay, so if we look at these two resonance forms right here, this one has 6 electrons at carbon. This one has 8 electrons at carbon, but most importantly, this one has an extra covalent bond. It's got a carbon-oxygen double bond. This is going to be the more important resonance form here, and this is called an oxonium ion. Again, like before, we can't ignore this less important resonance form. It does contribute, it helps us to understand the reactivity of this molecule. Nucleophiles attack oxygen, nucleophiles attack carbon in this compound, not oxygen. Okay, another interesting thing about this, a lot of people might be tempted to circle the compound on the left as the better resonance form. I've seen this a lot, and I believe that the reason they do it is because if you look at issue number 2, if the better resonance form places the negative charge at the most electronegative atom, shouldn't it be better to place the positive charge at the least electronegative atom? There might be some consideration of that, but as we'll see when we start looking at bond energies of things, when you have an extra bond, that's a very stabilizing situation. So the extra bond that you get by drawing the resonance form on the right makes it overwhelmingly the more important resonance form. Okay, all right, so there's our answers. Sorry, I didn't have to draw all those lines there. Okay, so here's a problem. Pause the video and try to do it yourself before I start going through the explanation. Write yes if they're resonance forms, and no if they are not, and if they are, choose the better one. Okay, so let's look at the first one. The first case, there are no connectivity issues. It's the same in both. There's nothing hypervalent. These are resonance forms. Yes, they are resonance forms. And the one on the right is better because it has an extra covalent bond relative to the one on the left. Okay, if we look at the next one, we would probably say, no, they can't be resonance forms. They don't even have the same formula. They don't have the same charge. It's kind of easy to exclude these as being resonance forms. They have different molecular formulas and obviously different connectivity. Okay, the next one is one that we're going to find in the second half of the class. It's a very important type of interconversion. But are they resonance forms? Well, no, they're not. They're constitutional isomers. Hydrogen is attached to a different atom in each one. Okay, so if we look at this molecule and compare oxygen and carbon, we see that they have different connectivity, so they can't possibly be resonance forms. Okay, we're going to do now just pull the proton off and look at the conjugate bases of those compounds. Okay, it turns out that these are resonance forms. Okay, there are no connectivity issues, and the one on the left is the better or the more important one contributing to its structure because the negative charge is at oxygen. But as before, we're going to find that the one on the minor or the less important resonance form actually is going to maybe go a long way toward explaining the chemistry of these systems. So we can't ignore the less important resonance form. It's just that both of these contribute to the structure, and the one on the left contributes more to the structure. Okay, we're going to spend a few minutes now talking about molecular shapes. And in organic chemistry, this is actually quite simple. It's governed by the rules called valence share electron pair repulsion, or VSEPR rules, meaning that the electron pairs involved in bonding in lone pairs want to obtain maximum separation due to the repulsions of the negatively charged electrons. There are only three geometries for organic molecules: tetrahedral, trigonal planar, and linear. To figure out the geometry at any specific atom, all we have to do is look at the number of atoms plus the number of lone pairs attached to that atom. Make sure to count the number of atoms and not the number of bonds. We'll see that when we look at a couple of examples. In the next chapter, we'll discuss how the orbitals, S and P orbitals, combine to make these geometries. And we'll have a better understanding why we're only going to count the multiple bonds once. Okay, so tetrahedral is a geometry we achieve when we have 4 atoms plus lone pairs attached to a central atom. Trigonal planar is what we get when we have 3 atoms plus lone pairs attached to a central atom. And linear is what we get when we have 2 attached atoms plus lone pairs. Okay? Alright, so when we look at the geometry, we're going to have to the screen here is a 2-dimensional surface, but we need 3 dimensions to fully describe the geometry. So we're going to use this symbol here, the bold line, or the line that gets bolder as x comes out, to signify that this x group is coming out of the screen. And we're going to use this symbol here to denote that the X group is going behind the screen or the paper. Okay, so let's look at tetrahedral geometry. This is when we have 4 atoms plus lone pairs attached to a central atom. The simplest molecule that shows tetrahedral geometry is this molecule called methane, CH4. Every bond angle is 109.5 degrees and equal to every other bond angle in methane. Okay, this is the tetrahedral geometry. The 4 bonds are as evenly spaced as you can possibly make them. Okay, if we look at how the atoms and lone pairs are arranged in water and ammonia, we also see they have roughly a tetrahedral arrangement of lone pairs and bonds as well. The oxygen lone pair and the oxygen lone pair or nitrogen lone pair in H angles are a little larger than 109.5 degrees. That's because the lone pairs are more repulsive, while the OH and NH angles are a little smaller than 109.5 degrees. But the deviation isn't really that large, and we can just refer to the shape as being tetrahedral. Okay, now the molecular shape is different than the electron pair geometry. I guess what I've been talking about here is the geometry of the electron pairs. The molecular shape of water is referred to as bent. However, if we look at the arrangement of valence electrons, it's tetrahedral. This last issue is going to be the more important one. Okay, we can say water is a tetrahedron where a couple of the bonds have been eliminated and replaced with lone pairs. Okay, if you look at the molecular shape of ammonia, it's going to be referred to as trigonal pyramidal. However, again, we have a tetrahedral arrangement of the valence electron pairs, so the electron pair geometry is tetrahedral. And again, this is the more important issue for understanding of the issues we face in organic reactions. Okay, trigonal planar geometry. Often in common jargon, people drop the planar and just state that it's trigonal. And this is when we have 3 atoms plus lone pairs attached to an atom. So BH3 is the simplest molecule that will show trigonal geometry. What we have is a planar molecule. All atoms are in the same plane and all bond angles are 120 degrees. These are as evenly spaced as you can get them. Okay, if we look to more organic molecules that would have the trigonal geometry, I have these two, formaldehyde, shown here, and ethylene, shown here. Okay, these are also trigonal planar at carbon. Okay, here's an important point. If you had just counted up the number of bonds plus lone pairs, of course you would get 4 for both of these, and you would say that they're tetrahedral, but they're not. So this illustrates why you have to look at attached atoms plus lone pairs, not number of bonds, okay? Because if you look at number of bonds, you'll always end up with 4, and you'll be saying tetrahedral for everything and getting the wrong answer unless it actually truly is tetrahedral. Okay, the other geometry we commonly have in organic chemistry is the linear geometry. That's 2 atoms plus lone pairs attached to a specific atom. Hydrogen cyanide is the simplest molecule that will show linear geometry. Okay, and so here the molecule is just existing in a straight line. I don't know why this pen is writing when it's supposed to just be moving. Sorry about that. Okay, so it's a linear molecule. It has a 180 degree bond angle. It really exists only in 2 dimensions. Okay, if you look up to this point, you could probably say double bonds give us trigonal planar geometry, triple bonds give us linear geometry, and to some extent that's true, but there is one other case where you can have a linear geometry. So carbon dioxide doesn't have any triple bonds, but yet it still has linear geometry. It has 2 double bonds coming from so the middle carbon here is part of 2 different double bonds. Okay, so that's also good for linear geometry. We refer to this structure of carbon monoxide as a cumulene structure. carbon dioxide rather. Okay. And acetylene is the simplest organic molecule that shows linear geometry. Okay. All right. Once we know let's do a problem here. Again, you should pause the video and do it for yourself. Determine the geometry and just restrict yourself to the terms linear, trigonal, planar, or tetrahedral. Don't worry about bent or trigonal, pyramidal geometries. Just worry about these. Stick to these three basic terms here. Do this for each atom that's not hydrogen or oxygen in this molecule. This oxygen is at the end of a chain, and its hybridization state is a little bit uncertain. Okay? Alright, so let's look at this molecule. Okay, so what you want to do is for each of these atoms, look at the number of attached atoms plus lone pairs, and that will tell you the geometry. Okay, so the answer here is, I'll just start from the end here, is that this nitrogen is tetrahedral. It's got two hydrogens, a nitrogen, and a lone pair. Four things attached to that one, so that's tetrahedral. This next nitrogen is trigonal. Okay, trigonal planar. I don't have any lone pairs. I've got a nitrogen, a hydrogen, and another carbon over here attached. This carbon is trigonal planar. Again, no lone pairs, a hydrogen, another carbon, and the nitrogen are attached. This anionic carbon, because it's an anion, we know that there has to be a lone pair right there. Okay, it's tetrahedral, and this is because it has attached to it a carbon, a hydrogen, and a lone pair. This is just a CH2 group. This is an obvious tetrahedron, as is this one, as is this one over here. Okay, this nitrogen here, there's a lone pair. It's neutral, so there has to be a lone pair. And this one would be trigonal. Okay, this nitrogen here looks exactly like it, so it's also trigonal. Okay, this carbon here looks like the carbon of CO2. Again, there's no lone pairs, and two nitrogens attached to it, so it would be linear. Okay, if we look here, because it's got a positive charge, there are no lone pairs. No lone pairs are attached there. There's only 6 electrons there, but there's 3 atoms attached, a nitrogen, a hydrogen, and a carbon. Thus, this compound, thus this carbon is trigonal planar. Okay, this last nitrogen, because it's got a negative charge and 2 bonds, it has to have 2 lone pairs. It's got 2 lone pairs, a carbon and another carbon attached to it. It's tetrahedral. And this last carbon is part of a triple bond, no lone pairs, oxygen and nitrogen is attached, thus it's a linear molecule. Okay, alright, so let's look at one issue associated with molecular shape, and that is molecular dipole. Molecular dipole is the vector sum of all individual bond dipoles. So if we look at hydrogen cyanide, it features a minor contribution from the CH bond and a major electronegativity difference between carbon and nitrogen, pulling electron density toward nitrogen. We'd say that the two dipoles work together and the net is to the right. If we look at formaldehyde, I'll just, in this graph here, I'll use the terms Y and x to describe my axes, and I guess z for the three-dimensional ones. What we see here is that the dipole moment in the y direction cancels out in formaldehyde, right? So these two basically cancel each other out in the y direction, but there's a slight net vector to the right, and thus the net dipole moment is toward oxygen. Carbon dioxide, we see that the bond dipoles are very strong individually, but they totally cancel each other out, so there's no net dipole in carbon dioxide. Okay, and this one here, it's kind of a complicated story. You see with the two chlorines, a very strong dipole, pulling the chlorines all by themselves, send the dipole in that direction, but what we see here is that the hydrogens are also kind of sending the dipole in the same net direction. So we have a strong net dipole in the direction indicated. Now if we have four chlorines, of course, in the tetrahedral geometry, the dipoles are going to completely cancel each other out. Okay, so there'd be no net dipole for a symmetrical tetrahedron. And let's just do this one as a last problem. Which is the more polar molecule of these two compounds shown here? And we'll go through this nomenclature business a little bit later in the class, but for now we'll just refer to this one as cis and this one as trans. Okay, which is more polar, cis or trans? Why? Well, cis is more polar because the dipoles work together and send the net dipole down in the cis isomer, but in the trans isomer, the strong carbon-fluorine dipoles oppose each other. We can see a similar effect from the carbon-hydrogen dipoles, which I didn't show. They're a little bit smaller, but they also are working to send the dipole in this direction in the cis isomer, but in the trans isomer, the dipoles are opposing each other, so there's no net dipole from the hydrogens or from the fluorines in this compound. Okay, at this point I am going to pause, or I'm going to stop this video here, and we'll look at the last video of this chapter in the part 4 video. Okay? All right.